This is a magnet floating, seemingly defying gravity, above something we call a superconductor. And as you can see, this isn't just your plain old repulsion at play, as the two objects don't want the distance between them to increase either. They just want to maintain some fixed separation between them. This is just one of the many peculiar effects of the phenomena of superconductivity, something that is still puzzling to physicists to this day. Even the giants like Einstein, Feynman, and Heisenberg, along with many more, had their go at it but failed to provide a satisfactory explanation. However, we have made significant progress and some remarkable discoveries along the way. This video series is aimed to dive into the story of this mysterious phenomena from the first discovery about more than 100 years ago to the present day. Let's begin the first episode of the road to superconductivity. Our story begins way back in the 19th century, in 1827, Cologne, Germany, where a certain someone had just shown, both experimentally and theoretically, the relation between the electric current flowing through a conductor, the potential difference across its ends, and its length and thickness. This certain someone was, of course, Dr. George Simon Ohms. This relation is now known to us as the Ohm's law, written in the modern notation as V is equal to IR, where V is the voltage or the potential difference, I is the current, and R is the resistance of the conductor. It is the quantity describing the opposition to the flow of electric current through the conductor. It has the unit ohms in honor of Dr. Ohms and the following formula, where L is the length of the conductor and A is the cross-sectional area and ρ is the resistivity. See, Ohms, while conducting experiments in his lab, had made a further discovery that not all metals conduct equally well. For example, he observed that a copper wire conducts electric current better than an iron wire of the same length and thickness. And this ability to conduct, or rather oppose the flow of current, is what this intrinsic property, the resistivity, is all about. What we mean here by intrinsic is that, unlike resistance, the resistivity of a material does not depend on geometric properties like length or the cross-sectional area. It is an intrinsic property telling us how good or bad a material is when it comes to conducting electricity. A material with lower value of ρ, like a metal, conducts electricity better than a material with a larger resistivity like an insulator. In fact, the difference between the ρ values of metals and insulators is huge, like 20 orders of magnitude huge. Now, when current is flowing through a conductor, it heats up, and the loss of energy due to this heating is referred to as power dissipation, which is also directly related to the resistance of the material. And generally speaking, like in the case of power transmission lines, you want to minimize this energy loss, and a conductor with low resistivity becomes extremely desirable. But what is it that determines the resistivity in the first place? Where does it come from? What do we know about it? Firstly, ρ or the resistivity is always positive. This comes directly from the second law of thermodynamics, which we're not going to get into this video, but the reasoning goes something like this. If you had a material with a negative value of resistivity, that would mean if you just made a little current flow through it and then leave this material be, the current would grow instead of dissipating away, and you will basically have an infinite source of energy, which is of course not something that the nature is going to allow for. It is forbidden by the law. Secondly, resistivity of a metal is an intrinsic property, depending upon factors like temperature and the purity of metal. The resistivity of a pure metal crystal is less than that of an impure or dirty metal crystal. Another thing that we know is that the partial derivative of ρ with respect to the temperature is positive, which basically means that the resistivity increases with an increase in temperature and decreases with a decrease in temperature. So the hotter a metal gets, the higher its resistivity becomes, and the cooler a metal gets, the lower its resistivity becomes. In 1897, Sir J.J. Thomson discovered the electron in the famous cathode ray experiment and also calculated the charge to mass ratio for the electron. In 1900, German physicist Paul Drude proposed his model for the electric conduction in metals. This is the model that most of us learn about in our high schools as to the reason for increased resistivity with temperature. What it basically says is that metals have free electrons and fixed lattice ions, and the electrons are constantly moving around and colliding randomly. And when we apply an electric field, the random electron motion is still there, but they collectively drift in one direction and we get current. Drude model says that the resistivity arises due to the energy lost by the electrons due to collisions with impurities, lattice ions, other electrons, and so on. It gives this expression for the resistivity of a metal, where tau inverse is the scattering rate or the number of collisions per second, and the reasoning for increased ρ with increased temperature goes something like this. At higher temperatures, the lattice ions begin vibrating more and start getting in the way of electrons and thus impeding the current. And therefore, this temperature and purity dependence of resistivity is captured in the scattering rate parameter in the expression of ρ. There are, of course, a lot of things wrong with this picture, and eventually quantum mechanics would be required to provide a more accurate microscopic model of electric conduction. However, we will develop a better picture of what really goes on according to modern physics as we go along in this series. But what would happen to ρ if we made a really pure metal crystal and then cooled it to an extremely low temperature? What do I mean by an extremely low temperature? How about in the vicinity of at absolute zero? 0 Kelvin or absolute zero is the lowest thermodynamic temperature possible. At 0 Kelvin, the system is in its state of minimum energy. It is not zero temperature on an arbitrary scale like the Celsius or the Fahrenheit scale, but rather an absolute scale. There is no such thing as a temperature lower than absolute zero, as the system is already in its ground state. However, we cannot just go ahead and measure the resistivities of metals at absolute zero, as it is impossible to reach according to the second and third laws of thermodynamics. How exactly? That is the topic of another video. For this one, know that a question like what happens to ρ at absolute zero is an abstract notion, as we are not going to be able to perform a measurement at it. However, with great efforts we can get close to it, as on the scale of temperature where the gases of air liquefy. And then at these temperatures, we can study what happens to ρ at such extremely low temperatures. This was one of the major questions of the time after the Drude model, and Lord Kelvin in 1902 had already put forward his prediction that the resistivity of a pure metal would first fall with decreasing temperature, reach some lowest point, and then start climbing to infinity towards absolute zero. The reasoning being that the mobility of electrons would also diminish at such low temperatures, and they won't really behave as free electrons of the Drude model. Knowledge through measurement was the motto of the Dutch physicist Dr. Kamerling Onnes, also considered as the father of low temperature physics. Onnes wanted to investigate the resistivity of metals at low temperatures. He wanted to do this using his state-of-the-art cryogenic equipment in his laboratory at the University of Leiden. The earliest investigations started with very thin wires of gold and platinum at liquid hydrogen temperatures. This was around 14 Kelvin, and before 1908, this was the lowest temperature available. At these temperatures, an almost linear decrease in resistivity and then leveling off to an almost constant value was observed. This strengthened the confidence in Lord Kelvin's prediction. In July 1908, for the first time in history, helium was successfully liquefied. This was a monumental achievement by Dr. Onnes and his team at the Leiden laboratory. It had taken 25 years of great persevering efforts of devoted physicists at the University of Leiden to create a plant capable of such a feat. Dr. Onnes basically had to become not only a scientist, but also a coppersmith, a mechanic, and a plumber to create and fit all the parts of the plant that he required. The first measurements for resistivity at liquid helium temperatures would take place in December 1910. The liquefaction of helium takes place at around 4 Kelvin. And to reach these extremely low temperatures, it is necessary to proceed by stages. This is referred to as a cascade in cryogenic labs. And for the liquefaction of helium at the University of Leiden, the cascade constituted of 5 cycles. The first cycle is of methyl chloride, leading to a temperature of minus 90 degrees Celsius. The second cycle is of ethylene, leading to a negative 160 degrees Celsius. In the third cycle, by means of liquid oxygen, the temperature is reduced to negative 210 degrees Celsius. For fourth cycle, the liquefaction of hydrogen helps us reach negative 259 degrees, and lastly, the most extreme temperature of negative 272 degrees is reached by means of liquid helium. This is only about 1 Kelvin above absolute zero. This is truly remarkable stuff, and don't forget that this is not modern day technology. This is more than 115 years ago. Onnes measured the resistivity of platinum at these extremely low temperatures. And what was observed was that the resistance of a platinum wire became constant below 4.25 Kelvin. This ruled out Lord Kelvin's theory, as he had predicted a minimum value and then a sudden increase instead of a constant resistivity. Onnes supposedly thought that the resistivity had fallen to a residual value that depended on the purity of the sample. And the Leiden lab had a lot of experience with purification of mercury. And since the liquid mercury in a capillary simply freezes at negative 39 degrees Celsius, contaminations due to drawing of thin wires could be avoided. On 8 April 1911, the measurement of resistivity of mercury at liquid helium temperatures would take place. This was a historic event. On this day, 2 new and very puzzling phenomena of nature would be observed for the first time by any human. As the temperature got cooler and cooler, the resistivity of mercury was decreasing linearly with temperature. This was just as expected. But guess what could have happened to resistivity at liquid helium temperatures? Do you think it suddenly started increasing, or did it just become constant, or perhaps it started doing something crazy like this? Well, it did do something crazy, but not this. 3 weeks later, Onnes would report his results to the Royal Netherlands Academy of Arts and Science. His report would be as follows. For the ultra-pure mercury, the resistance at 4.3 kelvins is much smaller than at 14 kelvins, but still measurable with this equipment, and it should still be dependent upon temperature. For the very low temperatures below helium liquefaction, it should become zero within the limits of the experimental accuracy. He concluded that these have been confirmed by the experiment. Luckily, we have the original lab notebooks of the experiment and know what had happened. Below 4.2 kelvins, that is, the liquefaction of helium, the temperatures had become very hard to control, and so the observations of resistivity had to be made really quickly. More on this later. At about 3 kelvins, the lab notebook reports the resistance of mercury to be practically zero. Since the controlling temperature had become a problem due to some reason, and practically zero could still be very small but a still finite non-zero value, like the residual value of resistivity Onnes was thinking before, and so there were further experiments done to seek clarity on these 3 queries. Firstly, on 23 May 1911, The experiment would be conducted again, but in a redesigned apparatus. It had the resolution to measure the tiniest of resistivity in the sample for the tiniest changes in the temperature. Instead of decreasing the temperature and measuring the resistivity, this experiment started from 3 Kelvin and started to increase the temperature slowly so the measurements could be made under more controlled conditions. The notebook entries tells us that the measurement read as follows. At 4.00 Kelvin, no measurable resistance and no indication of resistance rising either. At 4.05 Kelvin, nothing yet. At 4.12 Kelvin, resistance starts to appear. Onnes reported that within 0.1 Kelvin, the resistance of the mercury sample had increased by a factor of almost 400. This is crazy stuff, and there was no doubt about it. The resistance was literally too small to be measured, and really practically zero. And this change, this drop, was very abrupt, occurring at 4.2 Kelvin. The resistivity of ultra-pure mercury at temperatures below 4.2 kelvins is zero. This abrupt vanishing of resistance below a particular temperature, called the critical temperature, is the phenomena of superconductivity. It is essentially a phase transition of the metal from the normal conducting state at above the critical temperature to the superconducting state below the critical temperature. But how could this be? How can there be any such abrupt decrease at some particular temperature? Onnes and his team checked for all possible sources which could have botched up the experiment, like short circuits or any deformations in the wire connections during the temperature changes. But they could not find anything. We had no model at that time that was able to explain this, and for a long time, we won't have any either. This zero is very puzzling business. Think about it. It might be hard, but still conceivable to wrap your mind around something finite which rapidly becomes very, very small, like going from 1 to 0.01, but still non-zero. But how do you wrap your mind around something that goes from something finite to straight up dropping to zero, vanishing, not as in becoming very, very small, but as in nothing, as in no resistance, opposed to a very, very little tiny one? In fact, this won't be the first time Onnes would go after this zero to confirm if it's really zero. Like there is a plausible case that we just need more precise equipment to measure a very small resistivity. However, in 1914, it would really be settled that this is actually indeed a zero, no resistance at all. In the experiments of 1912, it was found that superconductivity wasn't a phenomenon which occurred in ultrapure mercury only. The resistance of the alloy of mercury and gold disappeared in the same way as with ultrapure mercury. Even for mercury amalgams that is used for backing of mirrors, the resistance would be found zero at liquid helium temperatures. However, the exact critical temperature for the transition varied. In a lot of experiments in the 1912 and 1913, the Leiden team would discover lead and tin to also be superconductors. The transition temperatures of these would be around 6 Kelvin and 4 Kelvin respectively. There was no theoretical explanation for all these experimental results. Superconductivity is the phenomena where the resistivity of a material drops to zero below a particular temperature. But remember how in the April 1911, where it had become very hard to control the temperature of liquid helium, and we know this from the entries in the lab notebook, the lowest temperature reached in that experiment was 1.8 Kelvin. And near this temperature, the boiling of liquid helium was suddenly replaced by remarkably strong evaporation at the surface, and the liquid visibly shrank. Without realizing it, the Leiden team had become the first humans to observe the superfluid transition of liquid helium. Superfluidity is the phenomena when a liquid flows with zero viscosity, that is, no loss of kinetic energy. It is a phenomena with its own very rich implications, just like superconductivity with zero resistance. It would only later actually be acknowledged and, I suppose, officially discovered in 1937. This dive into investigating the validity of our physical laws and models at extremely low temperatures had opened us to discoveries for which we had no explanation. I keep on saying it because whenever something so bizarre and strange like superconductivity appears in the pursuit of pure science, there are new explorations, new theories, new experiments discovering new effects, and new applications, and so on. It is very exciting and very puzzling at the same time. It opens the door for new science and is crucial for scientific progress. Remember the tricky business with the zero and zero resistivity? Onnes in 1914 concentrated on this conundrum. He was aimed to answer the question that if there is any tiniest of micro residual resistance in the superconducting state, how small would this resistance have to be to escape experiments just like it had been doing? He designed an experiment to measure the time it would take for magnetically induced current to decay in a closed superconducting loop. See, one implication of zero resistance is that it means that you can take a loop of superconducting material, put it in the superconducting state, by decreasing the temperature below the critical temperature, and put current through this loop by means of magnetic induction, and then remove the induction magnet and see what happens to the current. If this was a normal conductor, the current in the loop would decay in some finite time, actually very fast, as any resistance, no matter how small, would result in energy loss and thus decay of the current. However, for a zero resistance, like a superconductor, the current in the loop would continue to flow at the same value indefinitely, as a zero resistance implies zero energy loss. This phenomena is called persistent currents. In his experiment on persistent current, Onnes waited for the current to decay for an hour, but for a whole hour, there was not even a minute, not even the slightest decrease in the 0.6 ampere current in the superconducting loop. In 1932, Gerrit Flim, a member of the Onnes team, and someone whose name I'm sure that I'm pronouncing the wrong way, traveled from Netherlands to London, carrying with him a portable dewar containing a lead ring immersed in liquid helium. This ring had a persistent current of 200 amperes circulating in it. He made the demonstration at the Royal Institution, displaying that the current had now decayed on the route, and that the measurement of current via magnetic needles still yielded the observation of 200 amperes. Today, we have had currents persisting in the superconducting state for about 29 years without any measurable loss. If there was still a decay of current due to some super small resistance, then for the current decay to escape this kind of experimental observation, it would have to be so slow that the current decay time would have to be longer than the age of the universe. Persistent current, ever since Onnes' experiments in 1914, is the ultimate proof for the actual zero resistance for the superconducting state of matter. Persistent current is just one of the many myriad of effects coming out of the phenomenon of superconductivity. We will explore more of these like the Meissner effect, the Josephson effect, quantum locking and levitation as we continue on this road to superconductivity. But how does superconductivity come about? This discovery of superconductivity was before the advent of quantum mechanics. And yeah, there is some quantum stuff going on here. There is no doubt about that. But even using quantum mechanics does not give us a full explanation of all the experimental discoveries we have made so far about these superconductors. The upcoming episodes will shed light on some of these discoveries and our attempts to understand what is going on. As it turns out, there are many parallels to be drawn from the phenomena of superconductivity and superfluidity. Superconductivity is even often regarded as the superfluidity of electrons. We will talk about this more as we develop the concepts and the ideas in the upcoming episodes of the series. The next episode will be exploring the magnetic effects for superconductors, the Meissner effect in particular. Subscribe if you don't want to miss out on that, like the video if you liked it, comment, share with a friend, support the channel. Have a great day or night. Bye. See you in the next one.